In this screencast, we're going to talk about bases and coordinates of vectors relative to a basis. The idea, we're going to focus on the set of polynomials of degree 2 or less, which is just polynomials of the form a plus bx plus cx squared, where a, b, and c are real numbers. This set of polynomials, we're going to get a basis for it. And one way of looking at this set of polynomials is to say, oh wait, this is really just, I'm taking a number times 1 plus a number times x plus a number times x squared, which means this is really just the span of 1x and x squared. This set, 1x and x squared, is said to be a basis. 1x x squared is a basis for P2 of x. And why is it a basis? There's two things that you need to have a basis. One, the vectors, or these polynomials, are linearly independent. You can't write x squared as just some linear combination of 1 and x. You can't write x as a linear combination of 1 and x squared, and you can't write 1 as a linear combination of x and x squared. So they're linearly independent. And two, the vectors span the space. Anytime you have a set of vectors that are linearly independent and span a vector space, then we say that those are a basis for the space. So these are the two conditions it needs to have a basis. Well, once you have a basis, you can obtain coordinates. And I just want to give you an example. Let's take the coordinates of a vector. Let's say the vector is 3, 6, -7. Oh. The coordinates of a polynomial. We've got 3 plus 6x minus 7x squared. Well, why did I have that in there? Because the coordinates of this polynomial relative to that basis are, I need to take 1 times it by 3. I need to take 6 times it by x. I need to take -7 times it by x squared. These are the coordinates of that polynomial relative to the standard basis, which is this basis up here. So, now that we've got the example of what is a basis, it needs to be linearly dependent, span the space, and how do you get coordinates? It's really just the coefficients you have to multiply each of the basis vectors by to obtain your vector. We're going to change the basis. Is the set, and the set here is 1 plus x, 2x plus 3x squared, and 2 minus x plus 4x squared. Is this a basis for P2 of x? Well, if I want to know if it's a basis, then what I have to do is I've got to determine, are they independent and do they span the space? Well, to do that, the first thing we're going to do is we're going to rewrite each of these vectors using the coordinates relative to that basis. So here I've got a 1, and a 0. Here, there's no constant terms, so 0, 2 in front of the x, and a 3 in front of the x squared. And here I've got a 2, -1, 4. These are the coordinates relative to the standard basis. They're just vectors in R3. So really, I just need to know, are these vectors in R3 independent, and do they span all of R3? To answer that, I row reduce. Upon row reduction, I obtain the identity matrix. Well, what does that mean? 1, they are independent because every column has a pivot. 2, do they span the whole space? Well, they span R3 as vectors, hence P2 as polynomials. Because every column has a pivot, we know they're independent, and essentially because every row has a pivot, we know they span the whole space. So is it a basis? The answer to that is yes. Now we're going to look at just a different question. What are the coordinates of, we need a vector. Let's take the polynomial -4 plus x minus x squared. What are the coordinates of this relative to the basis up here. Well, relative to that basis, if I want to know the coordinates, that's the same thing as taking this matrix, augmenting it by the coordinates of this, and then row reduction. So what we're going to do is exactly that. 1, 1, 0, 0, 2, 3, 2, negative 1, 4. I'm going to augment by negative 4, 1, negative 1. And now I need to row reduce. So I row reduce, and upon row reduction, I already know I get the identity matrix when I row reduce this part. The key is what happens when I row reduce this last part. And row reduction yields a negative 2, 1, negative 1. Well, what does that mean? It means the coordinates of this vector relative to that basis are negative 2, 1, negative 1, which is precisely the same thing as saying negative 2 times the first polynomial plus 1 times the second polynomial minus 1 times the third polynomial should equal precisely the polynomial I started with. Here are our coordinates, and those coordinates come from our REF. That completes the